Hi, I'm Seth Chandler, professor at the University of Houston Law Center, and this video is on autoencoders. It's part of a series of videos for the course Analytic Methods for Lawyers, but my hope is that it is of interest to a broad audience. An autoencoder is essentially a way of being able to generate data that resembles the data used to train it, but that is not identical. Now, to do this, we're going to destroy information about the original data and then try to reconstruct what remains to resemble it. And if we do that destruction and reconstruction carefully, we actually end up with two useful products. The first is a way to reduce the dimensionality of data without destroying too much information. After all, if we destroyed too much information, we wouldn't be able to reconstruct the original. And second, by working in the space of the reduced data, sometimes called the latent space, we can use the reconstruction process to generate synthetic examples. Now, although conceptually you might be able to imagine an autoencoder that relied on one machine learning algorithm for information destruction and another machine learning algorithm for reconstruction, traditionally that's not what we do. We implement the whole thing through a neural network built out of components. I'm going to show you how to do that using the Titanic data. I'm also going to show you a problem with conventional autoencoders and show you how changing just one layer of that autoencoder can relieve the problem. This latter technique is called a variational autoencoder. We've used the Titanic data set many times in this course, and we're going to use it again. It's useful because we have intuition about it. It has just enough complexity to be useful without being so large or complicated as to distract. And our goal is going to be to create fake but realistic passengers on board the Titanic. And yes, we learned in an earlier lecture that you could actually do this with learned distribution, but I also want to show you how this versatile algorithm works. And by the way, a key idea of the algorithm, which is training a neural network and then using only part of the results and often throwing the rest away, is going to recur when we study computational linguistics, and in particular when we look at embeddings. All right, so as always, we got to start with the data. I'm going to use the data in the resource data form. We saw that, I believe, in clustering. I'm going to get rid of all the rows that have missing data. We don't need to deal with that level of complexity. I don't want the age to be in units. I want to make sure there's no order in the data. I want it to be column-oriented, so we're going to transpose it. I don't want it in a data set, so I'm going to take normal of it. And then, because class has a particular meaning, as you know in machine learning, and it gets ambiguous when we use class, I'm going to change the class column to read cabin. So it tells you what cabin class the passengers were in. So let's run that. And in just a little moment here, we will have our data in the right form. Okay, so there it is, and you can see here the classes of our passengers. Here's their ages, their sexes, and whether they died or lived. All right, now we're going to build this autoencoder in a modular kind of way. It's easier to debug them if they're modular, and also I'm going to want to swap in or swap out one of the modules and replace it with something else, and I don't want to have to re-architect the entire network. So here's the 5 modules. The first is what I'll call a representation graph that takes the raw data and creates a representation of it using many nodes. Here that'll be 50. There's a bottleneck graph that takes the output from the representation layer and shrinks it down to a very small number of values. This is the destruction thing I mentioned at the beginning of the video. I'm going to shrink it down here to just 2 values. And this shrinkage is sometimes called a bottleneck or a pinch point, thus the name bottleneck graph. There's a reconstructor graph that's going to take the output from the bottleneck, and it's going to attempt to create the same size data as the initial input. It's kind of like if you had a piece of pottery and you smashed it and you threw some of the pieces away, and you're an archaeologist, you might try to figure out, well, what does the whole vase look like? And that's what we're going to be doing here. There's a loss graph, which is going to tell us how to compute the loss between our original data and the thing that comes out of the reconstructor. If the vase looks like the old initial vase, well, we know we did a pretty good job, and if it doesn't look much like it, we know we probably need to change some parameters. But in an autoencoder, the initial data is actually its own target. Fifth, we're going to build a translator. And that's just going to take the numeric output from the reconstructor and put it in human readable form. So we start in human readable form like this, and we're going to end up in human readable form. Okay, let's get going. Let's build a representation net graph. We're going to need 3 encoders that are going to take textual data like this, first, female, died, and turn it into numbers, because as I mentioned in one of the early lectures on machine learning and neural networks, they don't know anything about text, they like numbers. So to do this, we're going to use net encoders, and I'm going to ask it to specify the output as a unit vector, meaning like if it's first class, it'll be 1, 0, 0, or if it's a female, it'll be 0, 1, or if they died, it'll be 1, 0. So let's build our encoders. Done. And now let's build the layers of our representation graph. We're going to have a catenate layer. We saw this before, I think, and we were doing neural networks for classification. That takes all the different pieces, the cabin, the sex, the age, the survival, and it puts it together in one big vector. Here it's not so big, it's just 8 members, 8 elements. We're going to have a batch normalization layer. We talked about that in an earlier video about how it's going to basically turn the data into a sort of, so it all has a normal distribution that makes it easier to work with. We're going to blow up the data with a linear layer to 50 nodes, and then we're going to need a nonlinearity. Here I'll use a very simple nonlinearity, the ramp function. So there we go, there are our layers. Now we need to hook it all up. All right, so here's what we got. We're going to take our 4 features, cabin, age, sex, survival status. These are the non-layer ports, and that's going to get fit into the catenate layer, and then that's going to go into the batch normalization layer, which is going to go into the linear layer, which is going to go into the non-linearity, and it's going to come out at a port which I'll call large representation. The other thing is this, and this is what we need to do an autoencoder, which is we need the output from the catenate layer to not go through any more changes, but to go directly to a port, a non-layer port called target. And we'll see later we're going to hook that output of target up to our loss layer, and that's going to be one of the things we compare in trying to figure out the loss. So let's do that. All right, and now we've got what we need. We're going to build our net graph with our layers, our edges, and then we're going to add in, here are the encoders that we need, and I'm going to say, could you make me a nice picture of the network? And so, there we go. You can see all of the features going into the catenate layer, which is going to send its output to the net port target, and it's also going to send it to the batch normalization layer, through to the linear layer, through to the nonlinear layer, and that's going to be outputted in the large representation. So just how you can see what it does, let's take our first 3 passengers, we'll initialize our representation net, and we'll see what the representation net produces. And you can see it produces a large representation. These are each length 50 vectors for each of the 3 passengers, and here's the first one, here's the second one, and here's the third one. And here are our targets. This is just really the input data that we have, and it's just being stuffed into the catenate layer and coming out of it unchanged. All right, so that's what the representation net is going to do. Now, once it's trained, these large representations will likely be different, but this is at least the form of output that we're going to have. Let's talk about the bottleneck layer. And a bottleneck is really what makes an autoencoder an autoencoder. The idea is to describe each passenger using very little data, the few shards of pottery, the few dinosaur toes. It's a form of dimensionality reduction, and it's basically a bridge between destruction and reconstruction. It's actually a very simple layer. It's just a linear layer that's going to produce 2 from 50, and then we'll add in a nonlinearity as we always should. And here, for no reason, I'll use the tanh function to create the nonlinearity. All right, so let's see. What about the connectivity? Connectivity is very simple. We have a large representation coming in. It goes to the pinch, it goes to the nonlinear part, and it goes out to 2 copies of the same thing. One I'll call compressed, and one I'll call latent. And one of them, latent, is used for inspection, really, and compressed is going to get passed on to another component, another module of the neural network. Well, we've got our nodes, we got our layers, we got our edges. Let's build the net graph. So here's our layers, here's our edges, and I'll tell it, look, the data coming in has 50 values, compressed and latent going out have 2, and information with full summary graphics says let's make a picture. So there's our picture. You can see what happens. Large representation comes in through the pinch, through the nonlinearity, and out pops 2 copies of what the nonlinearity produced to a port named latent and a port named compressed. So let's actually see what the bottleneck will do. Okay, first I'll generate the input that needs. I'll do that by running the 3 passengers through the representation net. All right, and now let's take that input and run it through the initialized version of the bottleneck. And there we go. So you can see we get our 3 passengers here, 1, 2, 3, just 2 pieces of data to describe the passengers, and latent is identical because that's how I defined it. Okay, so that's the bottleneck. Now let's do the reconstructor. The reconstructor has just 3 layers. We're going to blow up the stuff from the bottleneck to be length 50 again, stuff in a nonlinearity, and then shrink it down to 8. Why 8? Because our original catenate layer was 8, and so we want to compare what comes out of the catenate layer with what comes out of the reconstructor. So they both need to have the same length. Done. All right, let's look at our connectivity. We're going to take stuff in from a port called compressed. We're going to run it through the linear layer. We're going to run that through the nonlinear layer. We're going to run it through the second linear layer. And then we will take the linear layer and throw it out to a port called reconstructed. And we have everything we need to build our net graph. We got the layers, we got the edges, and we're going to tell it, hey, what's coming in has length 2. Let's make a picture. And now let's just make sure it works. We'll initialize our reconstructor net, and we'll pretend that we've got stuff coming out of the bottleneck. We know what comes out of the bottleneck might look something like this. There might be more stuff in it, but all we need is the compressed representation. And you can see that we now have 3, 1, 2, 3, 4, 5, 6, 7, 8, length 8 vectors, which is what we're going to need to make our comparison. Well, to do the comparison, we need a loss net. Loss net's very simple. 1 layer, a mean squared loss layer. Why a mean squared loss layer? Because we want to compare this value to the value that came out of the catenate layer for that passenger, this value for the second value that came out of the catenate layer for that passenger, this one for the third, and so we might as well take the sum of the squared differences and add them up, and then do that for all the passengers in the batch, and that's a pretty good estimate of how well our autoencoder is working. So there we go. Extremely easy connectivity. We're going to take stuff from the target and stuff from the reconstructed port and stuff it into the mean squared loss layer. So here's a picture of it. There it is, and we can see how it works. Supposing these are the target values, I'm just going to make them random. Here are the reconstructed values, I'll make them random. And if we do it, we get one loss because it's calculating the mean loss on each of the 3 imaginary passengers involved here. Okay, one more piece, which is a translator net. The reconstructor is going to give us a length 8 vector, and the computer is going to be very happy with a length 8 vector, but it may be hard to read for humans. And so what we want is output that looks exactly like the input, in which the cabin says first or third or second, and the sex says male or female. So we're going to create a little mini net graph that does this. We're going to need 3 decoders. These are basically the inverse of the encoders that we used earlier. And here are our layers. What we're going to do is we're going to take outputs 1 to 3 from the, basically it's going to be coming out of the catenate layer, or it's going to be coming out of, it's going to be coming out of the reconstructor layer. We're going to take the first 3 of those and say that's the cabin information. We'll take the 4th part, say that's the age information, the 5th and 6th parts, the sex information, and the 7th and 8th part is the survival information. Then we're going to pass the 3 things that are textual, the cabin, the sex, and the survival, through their softmax layers to turn those values into a probability distribution. So we did that. And now we just need our edges. So basically, we're going to take the input into the translator. We're going to take that input and throw it out to those part layers. And then the part layer is going to go to a softmax, which is going to then go out to a non-layer port called cabin reconstructed. Age is simple. It just goes directly to the age reconstructed port. Sex goes to a softmax, the sex softmax, which goes to another net port, non-layer port. And survival goes to the survival softmax, which goes to the non-layer port, survival reconstructed. So now all we do is we build our little translator. We have our layers, we have our edges, and we just tell it, look, the input's going to have 8 values, and in order to turn the output from the cabin reconstructed thing into English, you're going to use the cabin decoder, net decoder. For sex deconstructed, you're going to use the sex decoder, net decoder. And for survival reconstructed, you're going to use the survival decoder, net decoder. So I know that's a little complicated when I say it. Here's a picture of what's happening. This may be worth 1,000 of my words. Okay, like translator input's going to go, for example, to the survival. We're going to get the survival information out. We'll softmax it, and then we'll send that to a representation port. So let's just give an example of how it works. Here are 3 passengers. We have 8 values for each of them, and we're going to send it through to an initialized version of the translator net. And out pops English language descriptions of the cabin, sex, and survival, and the age we didn't have to do anything fancy with anyway. It already was a number. Okay, major prep work's done. Let's build our autoencoder. I told you, it's 5 pieces. Representation net, bottleneck net, reconstructor net, loss net, and translator net. And I'm going to give each of those layers names. So we're going to have a net graph that's in turn composed of net graphs. But that's very typical of the way neural networks work these days. They're basically nested neural networks. And there they are. Okay. Then we're going to have our edges, and let's look at this. The non-layer port called cabin goes to the input called cabin in the representation network. The non-layer port age goes to the age port of the representation network. The sex input goes to the sex input port of the representation network, and the survival status non-layer port goes to the survival status input of the representation layer. The large representation output from the representation layer goes to the large representation input of the bottleneck layer. The target output from the representation layer goes to the target input of the loss layer. The compressed output from the bottleneck layer goes to the compressed input of the reconstructor layer. The reconstructed port of the output port of the reconstructor layer goes to both the reconstructed port of the loss layer, and it serves as input for the translator layer. I know that's a mouthful, but basically what you can think of is we've kind of got, Lego pieces isn't quite right, but they're just pieces with hooks, and we're just hooking them up and using the names that are on the hookups of each part. So I think when we see a picture, you'll be excited. Here are the layers of our autoencoder. Here are the edges. It's all we have to do because we've already described the non-layer ports. And so here is a beautiful picture of our autoencoder. Here's the information coming in. The result of the catenation goes directly to the mean squared loss layer as one of the things it's going to be looking at. But we also send it to the batch normalization layer, which goes to a linear layer, which goes to a nonlinearity. Then we're heading into, in here, this is our bottleneck component, where there's a linear layer and nonlinearity. We'll send information out to the latent non-layer port. Now we're in the reconstructor, where we blow it up, another nonlinearity. We get it down to 8 layers, 8 nodes. The 8 nodes go, first of all, to the mean square loss layer to see how it compares with the catenate layer, and then to translate it into English, we send it to part layers, 3 of which go through softmaxes, and they all come out. Isn't that simple? All right, so let's just make sure that our autoencoder actually does something. We'll initialize it, and we're going to run the first 3 passengers to it. So let's see what we get. All right, we get our latent information. This is the 2-dimensional representation of the 3 passengers. We get our losses. They're huge because it's an untrained network. And now it's going to tell us, oh, I think they're all in first class. Here's their ages. That doesn't seem very good. Here's their sex. And here's whether they lived or died. And of course, these are not good values, but that's because we haven't trained the autoencoder. Once we train it, the hope is that we'll propagate back gradients to the parameters here that will force them to change, so that what comes out of this long process looks what comes through on this direct process. That's the concept of the autoencoder. Okay, let's do our training. Training code simple. Net train, here's our network, here's our data. All you remember says there are a lot of properties you can get out of a net train object. We want all of them. I'm greedy. So here we go. Ooh, look at that. It's diving. It's doing very nicely. We're getting more and more accurate. Our loss is getting lower. Our mean squared loss is a heck of a lot lower than 200 or whatever it was we had earlier. Looks like we're kind of stabilizing out here. A little bit of bumpiness, but that's okay. And we're done. We have our net trained result object. So let's just see how the first 3 passengers look. Here are our first 3 passengers. Here's information on them, and let's see what happens when I run our first 3 passenger through the trained net property of the trained network. And here are the ports that I want to look at: cabin reconstructed, age reconstructed, sex reconstructed, and survival reconstructed. And how do we do? We did great on age. We did pretty well on cabin class. Not so great on sex. And survival we did splendidly. So it is not a perfect reconstruction, and in fact, we did lose information when we moved from an 8-dimensional space to a 2-dimensional space, but we at least did it, and that's how an autoencoder works. Now for the cool thing, or depressing thing. Really, most of all that work was for nothing. All we want out of the autoencoder is the trained reconstructor, and maybe if we need it, the translator. And traditionally, you throw the rest away. The idea is that you now have a generator. You give it a few numbers, 2 numbers here, and it generates a synthetic passenger. It's a little bit like learned distribution and random variant. You now have a way of generating realistic fake passengers. And while, doing it in this simple context may not seem that impressive, but imagine If you could do this, as you can, for faces, where you come up with a low-dimensional representation of faces in the latent space, and you can use that to pop out faces that look real. Or music. You take music and you reduce it down to a few numbers, not two, but maybe 1,000 numbers instead of the million numbers that are actually in the music, and you pop out music that sounds maybe okay. And maybe in the not too distant future, autoencoders or similar techniques can be used to generate good fake realistic text. So let's see how we do this. We're going to use nettake to just get the part of our network that runs from the reconstructor through to the translator. So here it is. Here's our network, and we've just lopped off part of the big network we trained. And you can see that if we just give it two numbers, it will produce a fake passenger. And indeed, we can make a manipulate where I just vary those two numbers, and it will keep generating fake passengers. So, see, I'm changing its age, and if I go far enough, and I maybe move the x value a little bit, it should, if all goes well, there we go. All right, we just changed sex and whether they lived or died. And so, hopefully, we are, I may have to change the bounds of this, but we are able to generate faked passengers. There's another technique for doing this, by the way, called a GAN, a generative adversarial network. That's a more advanced method. We're going to look at it at the very end of the course, but autoencoders are tried and true technology for at least the simple scenarios. The other thing we could do, by the way, is extract a compressor. Look, we could take the representation component module and the bottleneck module, and if we put those together, we're going to get something that compresses data. Here's what it looks like. We start out with our input, and it goes into the representation layer, it goes into the bottleneck, and out it pops, in either looking at it in the latent net port or the compressed net port. So let's look at the latent representation of our first three passengers. And I could, in fact, take synthetic passengers. I could make up passengers, as I did here, and say, would you please tell me the two numbers that represent each of them? There we go. We built our autoencoder, but there's a little problem with it. Let's take a look at that problem. What I'm going to do is I'm going to run all of our data through it, look at the latent values and plot them. I can do that because it's just two-dimensional data. And what we see is there is a lot of structure to this data. It is not lying in some nice uniform space. And therefore, if I tell it, hey, I want you to generate me someone where the x value is 0.3 and the y value is 0.2, it's never really seen anyone like that before, and it's likely to give not very good results. Plus, even in between here, there are gaps that are likely to cause it to make mistakes. And so what we're seeing is a lot of structure to our output. That's actually not good here. What we want is compressed representations that are denser and more random. And that way, no matter where I go within sort of a ball of values that I might have, I'm going to get something that's similar to what the computer has seen before. The way to fix this, or a way to fix this, is called a variational autoencoder. It was invented in 2013, which is ancient history in machine learning land, and it's become quite popular since that time. If you want to read a long article, if this isn't long enough for you, here's a link to a quite good series of entries discussing the variational autoencoder, or VAE. Okay, all we have to do to build it is to swap out the bottleneck layer and put in a new bottleneck layer. And here's the idea. What we did before was we described a passenger deterministically with two coordinates. But how about instead we describe the passenger as coming from a product distribution in which, as it happens, both components are normal distributions. If you don't remember what a product distribution is, go look in the essays on 100 distributions to know and love, or the discussion of confusion matrices, but they're basically two distributions that produce numbers, but the two distributions aren't tied together. So to describe our two normal distributions, we need four values. Two for the means of each of the distributions and two for the standard deviations of the two distributions. So instead of pinching down to 2, let's pinch down to 4. Then we can use part layers to grab 2 of the values and use them for the means, and a part layer to grab 2 of the values for the standard deviation. And then we need a new layer, one we haven't seen before. It's called a random array layer, and what it's going to do is it's going to take a draw from the product distribution. The result is 2 values. We have 2 distributions in our product distribution. So when you say random variate of a product distribution with 2 distributions, you get 2 numbers, just like we did in our original bottleneck. The difference, though, is that now the relationship between the 8-valued input and the 2-valued latent representation is stochastic. But that, if you think about it, is exactly what you want to sort of fill in this area. If this point wasn't a point, but it was sort of a zone, and this point was a zone of possible outputs from a distribution, you would fill in the spaces and you wouldn't have all this structure that you see here. So that's the concept of a variational autoencoder, and let's actually go implement it. All right. Here's our VAE bottleneck layer. We have our pinch, but we're only pinching down to 4. We do need our nonlinearity. There's our tench. Now, let's send the first 2 values to be the means of the normal distributions that are components of our product distribution, and the second 2 values, the third and the fourth values, to be the standard deviations of each of those normal distributions. And here is our random array layer that's going to basically produce values out of normal distributions. If you're really puzzled, by the way, go read the documentation on random array layer, and it will explain in a little more detail than I want to do what's going on. Okay, here are our edges. Basically the same thing as before. We're going to take our large representation, send it to the pinch, send it to the nonlinear pinch, but now the nonlinear pinch is going to go both to the part layer here and the part layer there, and they in turn are going to get fed into the variate layer. That's the random array layer. The output from the variate layer is going to go, just as it did before, to the compressed port and the latent port. And also, in case we ever want to inspect what those means and standard deviations were, I've provided inspection ports for them. Now we can build our new bottleneck graph. It's the layers, the edges, okay? The large representation is still 50, that's what's coming in. The outputs are still 2, that's what's going out. And here is a very nice picture of our new bottleneck layer that's going to turn this into a variational autoencoder. Start with the not large representation, pinch, non-linear pinch, send part of that to be the standard deviations, send part of it to be the means. The standard deviation is going to go to a port, which is for inspection. The means are going to go to a port for inspection. They're both going to get fed into the random array layer, which is going to produce a random value that has 2 numbers. That's going to be sent to the latent non-layer port and to the compressed non-layer port. This compressed thing is in turn going to get fed in to the reconstructor, latently available for our inspection. So what I'm now going to do is I'll initialize our new bottleneck. We still need our representation net, and I'm going to take the first 2 passengers, give a representation of them, and now run them through the initialized bottleneck 5 times. And let's look at what comes out of the compressed value, the mu port, that's the mean, and the sigma port, that's the standard deviation. All right, so let's look at this. So the compressed values for the two passengers, here's one for the first passenger on the first run, the second passenger on the first run. Let's compare that to what comes out for the same passenger on the second run, different, third run, different, fourth run, different, fifth run, different. That's because it's stochastic. Similarly, the second passenger. Here's what comes out of them on the first run, but the second run, third run, fourth run, and fifth runs are different. But if we look at the mean port and the standard deviation port, yes, they're different for each passenger, but they never change for each passenger. Okay? That's because this is deterministic. This is determined by the representation layer and the pinches, and there's no randomness involved, whereas the compressed value is random, but it's exactly that randomness that we want. Now, let's build our variational autoencoder, and it's very, very similar. Representation net's the same, reconstructor net's the same, loss net's the same, translator net's the same. Only thing that's different is we've plugged in our snazzier bottleneck layer. It's thinking. Good. Our edges are exactly the same as they were before. Don't have to change a thing. And now we can build our variational autoencoder out of the layers, the edges. Don't need to do anything with the non-layer ports because they're already specified. And let's look at a picture of it. And there's our beautiful picture of a variational autoencoder. I think we should turn that into a t-shirt. And now let's go train our variational autoencoder. See if this poses any special issues. Let's do it. Okay, look at that lovely dive. The loss is getting lower. It's still a little higher than I'd like it to be, but that's because there's randomness there. That's all right. And so it looks like it's leveling out. It'll keep running for a while, but I think basically we have extracted what we can with our neural network. Come on, finish up. Go, little autoencoder. We're done. All right, so it took a little longer, maybe twice as long, but not so bad. Let's now get the generator out. To get the generator, we just take the reconstructor and the translator out of our trained net. There it is. Now, let's apply our trained net and see what the latent values look like and see if they kind of show that troubling structure that we saw with the conventional autoencoder. And they do not. Look at that beautiful ball. Look at that. They're just scattered. Maybe I should, let's increase the point size a little bit. Yeah, that's exactly the picture you want to see coming out of an autoencoder. We can move anywhere in this basically sphere or disk, and these are points that the autoencoder's seen before. And so, in fact, we can build a little manipulate to do that, and we can now move our little point, and we can see what happens as we do that. And we can see here we just changed, there we go, we just changed the class, cabin class, and if I move out, looks like we're changing the age a little bit. Not too much is happening out there. But in any event, we can now fill the space and generate synthetic passengers just as before. Okay, so you're probably wondering, in the past, I've shown you how to do the dirty work, and then I show you, oh, you can actually just do this easily with Wolfram language code once you know what you're doing. Well, with autoencoders, not quite. Yet, at least. You can use an autoencoder for dimension reduction. So here I'm going to take my Titanic data, boil it down to 2. I'm going to say, would you please build an autoencoder to do that? And you can see it does its little training. And it created a dimension reducer function, which we're going to apply just to the first 3 passengers. Right? We've got our 2 points for each of the 3. And now can we make a generator? So sometimes what you can do is you can say, hey, use my dimension reduction function, but use the compressed representation and give me back the original vectors. Let's see what happens when I try to run that. It says I can't do it. Why can't I do it? Because I don't know how to, I basically don't have a translator inside me. I don't know how to take those numbers and turn them back into second class female. So you can't really use an autoencoder exactly as you would want to here. I can try and trick it. So let's do feature extraction on the Titanic and we'll get numbers out. So we're going to get something that's going to take 4 input values and generate a length 8 numeric vector, just as our catenate layer did. Let's do dimension reduction on the feature extracted variant of the Titanic and use an autoencoder. And I'm going to do that once more where you can actually see the training. Let's do that one more time. All right, well, it happened very fast, and you can see it did some training. And now let's see whether it built a variational autoencoder or whether there's a lot of structure to the data. So we're going to look at the application of our dimension reduction function using the autoencoder to the feature encoded version of the Titanic data. That's a mouthful. And that is clearly not a variational autoencoder. That's a conventional autoencoder. And so using it as a generator is not going to work so great. We can try it. Like here, what I'm going to do is I'll compress the data and then I'll try and produce original vectors. And it will actually do it. But then if I say, well, would you use the feature extracting function and find the inverse of it and get me back something that's human readable, it's going to say, I'm sorry, I just don't know how. So for right now, if you want a high quality autoencoder, you're going to have to brew it yourself. Maybe later versions of Wolfram language will have more capabilities. All right, so what I showed you is what's called a generative method. The idea is to create, like with learned distribution, a vehicle for creating synthetic data. There is much more utility than you might imagine in doing this. It's not just fake faces, but there are many instances in which you want to see creative possibilities that you might not have thought about before. An autoencoder is one of several techniques to do this. We'll learn another one called the generative adversarial network later in the course. But what we learned in this essay is how to build an autoencoder and why a variational autoencoder can often be a simple improvement that gets you better generation of synthetic data. Thanks so much for watching.